Hello everyone, it's Salar and we are in part 36 of our tutorial, a tutorial to writing a real-time operating system. Finally, in previous part, I've started to talk about what's an operating system and what's a real-time operating system. As I've said in previous part, we want to run some process in parallel just by one CPU core. So I said we can do that by operating system or real-time operating system. I said the best scheduling algorithm for real-time operating system is preemptive round robin. But in this part, I want to talk about context switch. I don't want to talk about what's priority in an operating system, okay? By a simple operating system, I want to describe what is context switch and what the processor does when you have a context switch, okay, in round robin scheduling algorithm. So as I said, in operating system by round robin algorithm, we want to divide CPU timeline in constant size time intervals, for example 1 millisecond. I said you can do this in Cortex-M processor by sys-tick handler, okay? So assume that your processor is running the process 1. After 1 millisecond, by system-tick interrupt, the processor stopped running process 1. Context switch, do context switch, and jump to process 2. And start running process 2 for next 1 millisecond. After that, another time context switch to process 3, run process 3 another time for 1 millisecond, and finally after that return to process 1 and run the rest of the instruction after the last instruction, okay, for 1 millisecond and so on, okay? But in this part I want to say you what's under the hood in context switch, okay, and how you can do context switch, okay? But before describing what's behind the scene and under the hood in context switch, let's to see an example in Eclipse. So I developed a simple operating system, okay, to do just context switch. In this operating system, we don't have a thread priority, okay? Just we want to do context switch in each 1 millisecond, okay? I've developed this operating system in this file, system SimpleOS.c, this file, its header file, and this assembly file, okay? I have my system-tick interrupt handler in this assembly file, and whenever you have an interrupt in system-tick handler, the processor jump to this address, okay? This address is in a vector table, okay? Run these instructions, this assembly instruction, these two function, and after that return to the next process and context switch to next process, okay? For example, assume that in this operating system I just have two processes, process 1 and process 2, thread 1 or thread 1 or thread 2, okay? As I said, each thread is an independent function. For example, I have a function, almost bodiless function. In my function I just have a while loop. Another time in process 2, like before, just I have a while loop, okay? If you want to run these functions in parallel, you need to add them to the operating system by this function, okay? Create new thread has been defined in this file, okay? So for example, by calling this function I can add process 1 in this way to the operating system, set the name, set the desired name for that, and set the stack size for that, okay? I will say in next slides, each process needs to have a dedicated stack space. Okay, for example, for each of my threads I have 1 kilobyte stack. Okay, and after that start operating system. So let's debug this project. Okay, after OS start the system call, the processor jumped to process 1 because process 1 added to the operating system before process 2. First I've added process 1. So let's put a breakpoint in this line, or let's put the breakpoint in Y. Okay, after OS start, the operating system jump to process 1 and start running process 1 just for 1 millisecond. For 1 millisecond. For example, assume that we just have process 1 and we don't have process 3. Okay, run the process 1 for 1 millisecond. After that, to do context switch, jump to systematic handler. Okay, if I put another breakpoint here, remove this breakpoint, after 1 millisecond the processor jump to systematic handler and do context switch by these instructions and these functions. Okay, in next slide I will say what is increase OS tick value and what is context switch function. But if you run these instructions, after returning from systematic handler, the processor jump to process 2, context switch to process 2. Run process 2 for next 1 millisecond and another time jump to systematic handler to do context switch. Another time run, another time we are in systematic handler to do context switch. Now let's run these instructions for the second time, but in this time the processor return to process 1, and by this simple operating system and by using of systematic handler we can implement a context switch. But let's change this example and see the result on my board. Now I've added LED toggle and OS delay each 500 milliseconds in process 1 while loop. Okay, so I want to toggle and blink LED on my board each 500 milliseconds or every half second. Okay, and I want to send some string, for example here hello world, to the COM port of my computer, to the serial port of my computer by this function. In this project I'm using USART, one of my microcontroller, to send some information and some string to the serial port of my computer. Okay, and I want to send this string to my computer every 1 second, each 1000 milliseconds. Okay, so let's debug this project and see the result. Let's debug the project, start debugging and see the result. First, delete this breakpoint and start to run this process. So now let's see my board here. Okay, now as you can see I have blinking on my in this LED each 500 milliseconds. Okay, so let's do C serial port. I'm using qtcom terminal to see the sended string and sended data in my serial port in my laptop. Okay, if I open that, I have hello world each 1 second. Now my processor run process 1 and process 2 in parallel. Each 500 millisecond do LED blinking, and each 1 second send this data, this string to my computer. Okay, so here was an example about my simple operating system, but in this time I want to talk about what's context switch and how you can implement this simple operating system by yourself. Okay, so let's stop. See my desktop. Let's stop debugging and close that and return to my slides. Okay, now I want to say what's context switch, but let's talk about process state. In my simple operating system, each process has two states: running state and ready state. Okay, when the processor is running a process, for example, here, let's do it the way, for example, here processor. When the processor running process 1 is in running state, and process 2 and process 3 now is in ready state. Ready means they are ready to running. Okay, so for each process we have two states. We have other states in real RTOS, real-time operating systems, and I will give you a lot of information about process states in a real-time operating system in next parts. Okay, but in my simple operating system I just have two states: running state and ready state. But when a process is in running state, to do context switch you need to save some data of this process. For example, assume that the processor has running this process until this instruction here, and after that you have a context switch. You need to save the next instruction after this instruction, because here you want to run next of instruction after this instruction. So you need to save a return address to run rest of this process. Okay, so first you need to save address of next instruction. Okay, each process has a stack space, as I've said in my example. So you need to save a stack pointer of each process. So you need to save return address, stack space, and you need to save value of registers, because process 2 and process 3 will change the value of registers, and because you want to run rest of the instructions from this point, you need to save value of registers in this point before context switch. So before context switch we need to save some data: address of next instruction, process stack pointer, and value of registers. But there is an important point here. As I've said, we do and our processor does context switch by systematic handler, and when you have an interrupt, your processor write the value of these registers in stack. So by interrupt you have return address of next instruction, you have value of some registers, not all of registers. For example, you don't have value of register R4 to R11, and in this time stack pointer point to this address. Process stack pointer point to this address. Okay, so let's talk about register R4 to R11. Okay, because we don't have register R4 to R11. Okay, so as I said, when you have a function as a handler, you don't need to push register R4 to R11 by yourself in a stack, because this function do this fork, it's necessary. Okay, when you jump to an handler, this function push register R4 to R11 to stack if it's necessary for those registers that's used in these instructions. Okay, and when you return from an exception, automatically this function pop the value of these registers and restore the value of these registers. Okay, so in exception handling and in C function, you don't need to push these registers in the stack by yourself. Your processor push these values by exception in try, and your function write this register in the stack if it's necessary. Okay, for those registers that's changed in this function. But in context switch we have different situation. Why? Because necessarily your processor, when you have context switch, necessarily doesn't jump to the first of this function. Okay, for example, assume that you have, in this example, in previous run the processor has run this process until this point. Okay, and in this context switch and in this run and next run of process 2, the processor want to run this process from this point. Okay, but pushing instruction of register R4 to R11 is in the first line of this function, but you want to rerun this process from this line. And since these registers, and because these registers may change in these instructions, you need to stack register R4 to R11 by yourself. Okay, because pushing instruction of these registers for this function is in the start of this function, and in context switch you don't jump necessarily to the start of this function, and most of time you jump to the middle of the function. And for that matter, sometimes and almost all of times you return before ending of this function. And because pop instructions for these registers located at the end of this function, you need to do unstacking by yourself. Okay, but because in exception in try you jump to the start of a function and return from end of the function, you don't need to stack and unstack register R4 to R11 by yourself. But because in context switch necessarily your processor doesn't jump to the start of the function, you need to stack these registers by yourself. And since you don't know which of these registers has been changed, you need to push all of these registers in a stack by yourself. So stacking and unstacking register R4 to R11 is necessary in context switch by yourself. Okay, so as I've said in previous part, you have two stack pointer, main stack pointer and process stack pointer. Always main stack pointer point to this address, point to the main stack pointer. Assume that here is your string. But I said you can have other stack space, for example in your heap memory. Okay, for example, assume that I have n processes, process 1 to process n. For each of my process I have a stack space. When the processor running process 1, the stack pointer or PSP process stack pointer point to this address. When the processor running process 2, PSP point to this address, and when the processor running process n, PSP send to this address. So by context switch you need to change the value of PSP. Okay, well, so let's have a closer look on context switch in my operating system, in my simple operating system. Okay, assume that you have just two processes, process 1 and process 2, and the processor is running process 1. Okay, assume that the processor is running process 1. We are not dealing with this part in this time, and pay attention to this part. When I said for each process you have a stack space, for example, assume that here is process 1 stack space. When the processor running process 1, PSP point to the process 1 stack space. Okay, for example, assume that process 1 point to this address, for example. But assume that the time of this process has been done and you want to have an systematic context switch by systematic handler. So I said for context switch the processor jumped to systematic handler, to this function, okay, to this assembly function here, to this assembly function. Okay, when the processor jump to this interrupt or exception, push some value of registers in the stack. Okay, so in this line you have some information in stack. You have value of R0, R1, R2, R3, R12, LR, return address, address of next instruction, and process status register. Okay, in your process 1 stack space. And now PSP point to this address. Okay, but I said you need to push register R4 to R11 by yourself in a stack to preserve this value to the next run, for next run. Okay, so after that your processor running this green part, these instructions. By this instruction, first you write the value of PSP and a special register. If you want to write a value of a special register to general registers, you need to use this instruction MRS. Okay, so by this instruction your processor write the value of process stack pointer, this value. in register R3, write or push R4 to R11 stack by this store multiple decrease before instruction, and after that write the value of new stack pointer to PSP. Okay, we need to write the value of link register. For example, here is 0xFFFFFFFD, because in my processes I'm using a process stack pointer. Okay, here is T, here is not 9. So by running this green part, we need to write the value of link register in stack, because your processor changed this value by jumping to these functions. Okay, so but after running the green part in system handler, after running green part, you have the value of register R4 to R11 in your stack. Now PSP point to this address. Okay, after that you need to run these two functions. What's these two functions? First is increase OSTick value. OSTick value is a counter in my operating system, and by each jumping to this handler, this function increase the value of this variable by 1, because each 1 millisecond my processor run this function. By this function I can measure the time. Let's just see this function. Here is a simple function, increase OSTick value. Here is a variable in my operating system, and in each running of system handler I increase the value of this variable by 1, and in this way I can measure the time, okay, in millisecond. So after returning from this function, the processor run context switch function in my operating system. So what does this function do? First, save the value of process1 stack pointer in memory. Okay, star SP means that you have this value in memory. You have a stack pointer in memory. As I've said, you need to save the value of stack pointer. Okay, so in this time, if you save the value of stack pointer, this value, you have the value of all of your registers and return address. So by just saving this process stack pointer, you can save all of data that you have need to do context switch. So first, write the value of process1 stack pointer, now PSP, in memory. And after that, change the state of process1 to ready. Let's just see the function here. As you can see, here is context switch function. First, get the value of process stack pointer and write that in thread current stack pointer, because current running thread in this time, I will give you some information about this structure in next part, but assume that in this time, in this variable, in this address, I have the current running thread. For example, here process 1, and in this structure I have a variable thread current stack pointer. I can save the value of PSP in that to use this stack pointer for next running, and change the state of current running thread to ready. Okay, first running these two line of code. After that, select next running thread. For example, after that I want to run process 2. Okay, select process 2. Okay, So here, if the running process is process 0 in this list, in the list of my thread, the next current running thread is process 1 or thread 1. If the current is 1, the next is 0. Okay? After running process 2, another time run process 1. Okay? So select next running thread and write the value of process 2 stack pointer to PSP. Okay? Because I want to run process 2, I want to write the value of this address in process 2 stack space in PSP from memory, and change the state of this process to running, and change the state of process 2 to running. Okay, so after that, change the state of new current running thread to running and set PSP by process 2. In this time current running is process 2 because I've changed this variable by this code, by this if and else code, and write the current stack pointer of process 2 to the PSP. So by running context switch function, now I have this address in memory. Okay, the process 1 now is in ready state, but now PSP point to this address. Okay, and process 2 is in running state. After running context switch function, now I can restore these registers to this value to the registers and return to the return address. Okay, I have address of next instruction here. So now I'm in this line and here, and now the processor run the red part. Write the value of process stack pointer to R3, pop value of register R4 to R11 by yourself, and write the value of new stack pointer to PSP, process stack pointer. Now after running red part, the processor and the systematic handler pop value of register R4 to R11, pop this value to the registers. Now process stack pointer point to this address. Now by running this instruction, the processor write the value of 0xFFFFFFD to the PC. So the processor pop this value from stack pointer to the registers, and now process stack pointer point to this address, and now the processor running process 2 and process 1 is in ready state. So by this code, these instructions and these two functions exactly, especially with this function context switch, we can do context switch and switch the running process from one process to the next process. Okay, here was a so simple real-time operating system that just do and just does context switch in each 1 millisecond. Okay, in next part I will give you more detail about other functions, for example, OS initialize, OS start, and create new thread. Okay, and complete the subject of this simple operating system. And after that, start to developing a real-time operating system, a real RTOS that has a lot of facilities, not just context switch. Okay, so thank you very much to see me, and see you soon in the next part.